Okay. So, chemists, this is going to be another slightly longer lecture. And this one goes along with the representative particles that we talked about in class today. So, let's do some purple. Pure substance. What is a pure substance? So, this is a sample of matter. We're going to do a bunch of vocab to start. A sample of matter made up of the same particles arranged in the same way throughout. Now, this doesn't mean it has to be an element, right? A pure substance just has to be a pure substance can be an element or a compound, but it just has to be the same composition throughout. So, an example of this. Oxygen, if I just had oxygen gas, that would be a pure substance, just made of O2 molecules. But if I also had a sample of just pure table salt, pure sodium chloride, well, that is also a pure substance. Yes, it's made up of positive Na ions and positive or negative Cl ions stuck together. But because the particles are arranged in the same way throughout, that alternating plus negative thing, matrix that we talked about, and there's nothing else involved, it's a pure substance. Now, if I dump NaCl into water, all of a sudden I have a mixture, and it's no longer a pure substance, right? So it has to be the same stuff throughout. Element is the simplest substance. These are the simplest substances. So all the atoms in the substance have the same number of protons, right? So if I have a sample of pure iron, right, all of the atoms will just have 26 protons. If I go back to my sample of pure oxygen gas, all of the atoms will just have 8 protons. Okay, so element, all the atoms have the same number of protons. And a compound consists of 2 or more elements bonded in a regular pattern. So going back and throwing some examples in here, just for elements would be like iron, oxygen. Compound example would be sodium chloride, water, things that have 2 or more different elements bonded in a regular pattern. Okay. So, atom. Now let's go back to the purple. Atom is a neutral particle. Remember, we're talking about particles now and the different ways we can describe pieces of matter. Particles are like a catch-all word, right? But we're breaking it down a little bit more deeply into the individual ways we can discuss them. So an atom is not a neutral particle. It's a neutral particle made of protons and neutrons in the nucleus and surrounded by electrons. Okay, the next type of particle we're going to talk about is a formula unit, which is the only time you can ever curse at a teacher is when you're talking about this type of particle. And this is one set of ions that make the chemical formula for that substance. So an example here. For calcium chloride, one formula unit is 1 Ca2 plus ion and 2 Cl minus ions. Remember, if I have calcium chloride and it's a solid, it's all in this matrix of alternating plus and minus charges. One formula unit is just one set of ions that make up the chemical formula. So a molecule is a group, I know we talked about this already, of atoms covalently bonded together into a single particle. Okay, so now let's summarize the bonding stuff again. I know we've sort of been doing it to death in class, but I want to make sure we understand it. So, summary of metallic bonding. The valence E minus are shared by everyone. So only metal atoms. The valence electrons shared in a common pool. And examples of this are like copper, gold, etc. All right. So again, this might be one of those days where you're going to go over in notes, and that's totally cool. So, property of metallic substances. State of matter. Usually solid. Almost always solid at room temperature. The exception being mercury. Do they conduct electricity? Yes. Because the shared E minus are free to move. Now, in order to have electricity, or for conductivity, charged particles must move. And in the case of metallic bonding, it's obvious that the positively charged nuclei can't move. It's just the negatively charged electrons that are free to flow. And do they dissolve in water? No. No. Metals don't dissolve in water. Okay. Ionic bonding summary. Strong nonmetal atoms steal a valence electron or more from metal atoms. Creating plus and minus ions. The ions, positive and minus ions, are strongly attracted to each other. And arrange into a repeating pattern. And examples here would be sodium chloride is the most common one that you guys are aware of. So again, we have our positive ion and our negative ion, and then they're alternating with plus attracted to minus. So another way to look at it is, if I just look at this one cation here, it's attracted on all sides to the negative ions around it. So it sort of locks into place. And if I look at the negative ion next to it, same thing is true. It's attracted to all the positive ions around it, so it's locked into place. So that the attraction between the ions locks all of the ions into place. So, properties of ionic compounds. State of matter, they're solid until very high temperatures because of the strong attraction between ions. So, now, do they conduct electricity? When they're solid, no. Remember, the ions are locked into place when they're solid. So, in order to have electricity, conductivity of electricity, you need to have moving charges. So, do they dissolve in water? Yes, with some exceptions. Mostly they do. And does the solution conduct electricity? Yes. Because now the ions are free to flow. Again, every year I explain this over and over. It doesn't have to do with the metals, right? The fact that ionic compounds contain metals is not the reason they conduct electricity. The reason they conduct electricity is because the positive and minus split apart in water, and both of those charged particles can carry electricity. So the reason they conduct in water is because both ions are free to flow, the metal and the nonmetal. All right, covalent bonding summary. Here, non-metal atoms share valence electrons between two atoms at a time. Now, this on the left, this is the molecular covalent. And this is network on the right. So what is the difference between the two? Well, here, you notice there are no bonds between molecules. Right, so if you think about this as, say, hydrogen, H2, you have the attraction of nuclei to shared E minus. So you have the positive nuclei and the shared electrons. But you don't have that same level of attraction between different hydrogen molecules. So examples here, well, yeah, we'll do examples here. Examples, water, oxygen, and sugar, which C6H12O6. For network, well, instead of forming discrete molecules, what happens is you have the positively charged nuclei of one, and this only happens with carbon and silicon, really. There are a few others. But they're all attracted in a big matrix to each other. So each one of these atoms shares electrons with its neighbors, but only its neighbors. Right? It's not like a metal where they're free to flow. These electrons are locked into place between the two atoms, right? So both of those atoms are pulling on those electrons, so those electrons are locked into place. The major, why we don't talk about these as much is because there are only a few examples that are well known. So diamond, which is just solid copper or graphite, and then quartz, which is SiO2. But if you think about diamond, what are the things you think about when you think about diamonds? Yes, how expensive they are. But also maybe you think about how hard they are, right? And they're so hard because each of those covalent bonds are so strong that those atoms don't want to move. That's what makes diamonds so tough. All right, properties of network covalent substances. Back to the purple. State of matter, solid. Just, they're solid. Do they conduct electricity? No. Do they dissolve in water? No. They don't conduct electricity. Those charges are locked into place. Those electrons are locked between the atoms, so they are not free to flow. They do not dissolve in water. They're very strongly attracted to each other, so they do not break apart. Molecular covalent substances. State of matter can be any. Solid, liquid, gas. Depends on the molecule. Depends on, obviously, the temperature. You think about water, you have ice, liquid water, and water vapor. Do they conduct electricity? No, because the charges are not free to flow. Do they dissolve in water? Maybe. Some do, some don't. I'll keep you in suspense. We'll learn about why later. And does the solution conduct electricity? No. And no free-flowing charges, which is what you need to conduct electricity. All right, and that is it. So we're going to do the unit review in class, and you will be testing very soon.